Okay, before I start the concept of digital circuits, I want to tell you what is Boolean algebra. Okay, so Boolean algebra is used for analyzing and implementing digital circuits. Okay, implementing digital and understanding also digital circuits. Okay, a Boolean algebra only allows two values. Okay, 0 or 1. Normally, this is called as a false value. This is called as a true value. Okay, 1 is called as a true value. Now, when you say false, what you mean is, sometimes you will see the word as off. Okay, you will always see the word no signal. You can also see words like open switch. Okay, open switch. So you can see these words when you talk about the false. So these are one and the same thing: false, off, no, open switch. And sometimes you can also see low mentioned. The value is low. All of these is 0, right? And supposing you see you see the true, which is 1, you may see words like high. The signal is high. A yes. Okay. If it is off, here it will be on. You may also see closed switch, right? So this is 1. So all our digital circuits are based on Boolean algebra. Boolean algebra only allows two values which serve as inputs or outputs for a digital circuit. And the words which are used for false, the alternate words which you may see in questions are off state, no, yes and no instead of false and true. So 1 is a true value, right? 1 is a true value. You may see a yes. You may see an on. 1 can also mean on. Open switch may indicate a low value. So be very careful when you're solving that. A lot of Boolean terminology may get used while you study the digital circuits, right? So Boolean algebra obviously is a mathematical concept, but it is closely linked to the digital circuits that we study. Now let's proceed with the logic gates, variety of logic gates, and understand what they are. So all right, so let me just tell you what is a logic gate first. A logic gate is a device. Okay, it's a device, and it is the building block. It is the building block for all digital circuits in the world. So, your mobile phone, your laptop, all are digital devices. What are they made up of? Okay, they are made up of, so the digital devices are made up of multiple logic gates, right? So, a logic gate is also a device, and then multiple logic gates come together. A lot of logic gates come together to make a digital device. And what is the logic gate made up of? A logic gate is made up of diode. A logic gate is made up of transistor. And the third important element, which is always there in a logic gate, is also a resistor, right? So these are used, multiple types of diodes. I have a lot of video lectures on diodes. There are many types of transistors, resistors. All these three come together, and what they create is something called as a logic gate. Then lot of logic gates come together and create what is known as a digital device. What is an example of a digital device? Laptop, PC, mobile phone, everything nowadays is digital. In fact, your bulbs in the house, the curtains in the house, everything is becoming automated and is a digital device. So I hope at least on definition level you're clear as to what is happening, and the terminology of digital device, logic gate, and what is logic gate made up of is clear in your mind now. Thank you. Let me just start with the first one. And these are the basic ones. The basic ones we study in this chapter. The gates that you study, the logic gates, right? The word used is the logic gates. The logic gates we study, right, are three types, the basic ones. Okay, the first is the AND gate. This is a very basic. I will explain you what is an AND gate later. The second important one you learn is the OR gate, and the third one that you learn is an AND gate. Sorry, not the AND gate, but the NOT gate. Let me call it a NOT gate. So AND gate, OR gate, and a NOT gate are the basic ones. If you have these three available to you, 1, 2, and 3, using these three, you can build other types of gates. So use these three, combine these three, and you will be able to get the other types of gates, which you might have heard about. The NAND gate. A NAND gate, for example, which we will study, is nothing but a combination of NOT gate plus an AND gate, right? So currently just focus on one thing, that these are the basic gates. By using these three basic gates, you can get any other gate. We will also study about NAND gate. We will also study about NOR gate. We will study about XOR gate. All the other gates which are complex in nature can be obtained by combination and permutation of these three basic gates. Right? For example, I told you NAND gate is made up of NOT plus AND. You use two digital basic logic gates to build a complex logic gate called as NAND. We will now study each one of them in detail, and then we will try to understand what do they do. Thank you very much. Right, good afternoon. It's very cold here, and today I will talk about the concept of the logic gates and the truth tables. Okay, so we will study semiconductor. Digital devices are based on the concept of logic gates. So let's talk about logic gates and truth table associated with the logic gate. So truth table. So let's start with the important ones. The first one is the AND gate, right? So the first one is your AND gate, and it is represented with X dot Y. Okay, and the truth table for AND gate is if you have X and Y, X and Y. Okay, let's put the value 0 and 0, which means both X and Y are false. Then what is the output? So the output which comes from this gate is 0, 0 and 1, which means this is false and Y is true. The answer is going to be 0, 1 or 0, again 0, 1 and 1. The answer is 1. So we started with an AND gate. The logical representation of an AND gate is this. Okay, so this is the way a AND gate is represented. X and Y are two inputs, and on this side you get an output. Okay, so this is the AND logic gate. This is the way it is written in Boolean. This is the schematic representation. This is the way the truth table is drawn. So the truth table is this. Okay, so I can just convert this into a truth table, right? So this is the output comes only when both X and Y are true. So you can see, right? X is true, Y is true. Only then the output is 1. In any other situation where X is false, Y is true, y is false, y is true, x is false, the answer is no output is received. Okay, so this logic gate concept is when you have inputs coming in and what is the output. So the output is this. Okay, this could be a signal in the context of a semiconductor device. Okay, so let's talk about the second one. The second famous one is the OR gate, right? Now the OR gate is represented by this. Okay, and if we talk about the logic of the gate, the truth table of the gate, this is the way it works. So if you have in two inputs which are coming, right, and if we have to draw x and y, and let me just complete this one also, because the last column is the output. Okay, so x, y, and this is the output. This is the output. Okay, so let's say x is 0 and y is 1. Either any one of them is 1, right? The input signal is available, and the other one is false. So y is true, x is false. Any one is 1, true, you will get an output, right? So this is the output, which is this. If now x is true, y is false, still the answer is 1. Either one of them could be true, you will get a true answer, which is you will get some output. Then let's talk about both being false. You will get nothing. If both are true, the answer is true. So this is the way the gate, which is called as the OR gate, works. And the way you represent an OR gate is this, right? You can see the representation of an OR gate is done like this. So this is your x, this is your y, and done. So this is the truth table for an OR truth table, right? So what is the difference between AND and OR? In AND, both have to be true. Both have to be true, only then you get a true. But in the case of OR, if one is true, that is enough for you to get a true answer. So you can see here only y is true, answer came. Only x is true, the answer came. Both are true, excellent. But in this particular case, which is AND, you get an answer as 1 true only when both are true, right? If one is false or both are false, you always get a 0. This is a very important concept which you must know. Very basics of logic gates should be known to you, because you can do some complicated exercises based on this. A lot of digital devices which you use on daily basis are based on these only. Okay, so we will talk about logic gates as we progress. Then let's talk about the next one, right? The next one is called a simple one, which is a NOT gate. Okay, a NOT gate is something which converts true into false. So let me just show you how you represent it. You have a single signal and you just make a line on top of it, right? So what it will do is, whatever the input value you have, it will reverse the sign of that value. So let's say you put the value of x and you get an output because you have inserted a NOT gate. So in the middle of x to xy is a NOT gate. So you give it 0, the output will be 1. You give it 1, the output will be 0. So it always reverses the signal. This is called as a NOT gate. Now let's talk about one more. The next one is called as a buffer. Okay, a buffer. Let me just write BUFFER. A buffer is a logic gate which gives you the same answer which you apply as an input. If you apply it true, so let me just write F and let's get a buffer. This is the buffer, X buffer. Let's call it X buffer. If you give it 0, it will give you 0. If you give it 1, it will give you 1. So the buffer gate is also used sometimes, but we are not here to discuss the applications. So initial level, what you must understand is you have four types of basic gates, out of which this and this you will see often. Sometimes you may also see a buffer gate, and you will have to immediately work and say, okay, buffer gate makes no difference, because the output which you get in a buffer gate remains the same. The output you get in a NOT gate is reversed, right? So this is a reversal type of gate. It will reverse the whatever input you give it. If you give it true, it will give you false. So when I say true, I mean one, and I when I say zero, I mean false. So I hope these basics, the AND, OR, NOT, and buffer are clear to you. Let's move to the advanced level logic gates, which are built using these only, but some combination and changes are made. Let's move and talk about them. All right, just one point which we missed was, what is the sign of a NOT gate? Okay, so this is the sign of a NOT gate. So when you give it X, the output is X NOT. So this is your NOT gate, right? I hope you've understood. We missed the sign, and I've put the sign also now. Right, so let's move towards the next logic gate, which is called as a NAND logic gate. Okay, NAND, NAND, and you can see the there is an AND inbuilt inside this, right? So how do you represent this? You represent it X dot Y, but what you do is you draw a line on top of this. So X dot Y is what? An AND gate, right? And to make it a NAND gate, what you do is you draw this bar. Now, when you make it a NAND gate, what you need to do is the sign also needs to change. The sign also needs to change. And what you need to do is add a circle here. This will make the AND gate as a NAND gate. Okay. And these are the two input signals coming as 0 and 1. What a NAND gate does is it is just reverse of an AND gate. So if you draw the truth table X, Y, and X dot Y, right? And if I draw a table here, if X is 1, Y is 0, 0 means false. In an AND gate, the answer would be 0, because for AND gate, you cannot have any false situation. If there is a false situation among the two, between the two, the answer is 0. But a NAND gate will be reverse of an AND gate. So if the answer for an AND gate is 0, the answer for a NAND gate is 1. Let's put false and true. Again, the same situation. For an AND gate, the answer would be 0. But for a NAND gate, the answer is 1. Now let's talk about both being 0. Logically, AND gate, you need both to be 1 to get the answer as 1. But in this case, if both are 0, the logical answer is 0, but here it will be 1. So if you have both as 1, an AND gate will give you 0, but this particular logic gate will give you 0, right? So this particular gate, the NAND gate, is reverse of an AND gate. So you can compare the truth tables of these two. I'm just completing the table, and you will realize yourself that it is very different from AND gate, and you should reverse the answer which you get and convert it to just reverse of what you get in a AND gate. All right. So let's talk about the next one, which is also a very interesting one. The next one we studied was a OR gate previously. Now let's study the one which is called as a. All right. So the next important gate we will study is the NOR gate. Okay. It is reverse of, it's called NOR, NOR, right? You can see this OR and an N. So you write OR gate as X plus Y. Draw this line on top of this. This makes it a NOR gate. And now what you do? You X, Y, and this particular circle makes it a negative, right? So a NOR gate is also a reverse of OR gate, right? So this is a reverse of an OR gate. Okay, let's draw the truth table. So I will just draw X, Y, and the output, which is X plus Y. Okay, so let's complete this table. And so X is 0. So in OR gate, you remember if any one of the two is 1, the answer is 1. But a NOR gate is reverse. The answer will not be 1, the answer will be 0. Now 1, 0, either one is 1, right? The answer in an OR gate should be 1, but here it will be 0. Let's talk about both as false. If both are false, answer anyway has to be false for an OR gate, but this is a reverse gate. So you can see 1, right? And now let's do one thing. Let's have both as true. And now OR gate, very good condition. If both are true, answer has to be true. But for a NOR gate, this will be 0. So you can do a small comparison and see that a NAND gate, also has something very similar where both are 0, the answer is 1. And in the case of an OR NOR gate also, both are 0, the answer is 1. So here lies the commonality between the two gates, that they behave in a very typical manner in certain situations, right? It doesn't mean you will use NOR gate instead of NAND gate, because the other two conditions of a NAND gate are way too different. So I hope the NOR gate is also clear in your mind. Let's move to the next type of gate, which is again a very important type of gate. All right, so the next one is a very important gate, XOR gate. This is also called as an exclusive OR gate. Okay, and the way output is given is A dot B plus B dot A. And if you put a dash on top of something, it becomes reversed, right? The quality of and sometimes it is also represented as A and a circle and a plus and a B. So this is one and the same thing from representation point of view. This is a XOR gate with two signals coming in, right? Now, the XOR gate, the output is 1. Output is 1. Output is 1 when the number of true inputs it receives is odd. Okay, odd number of true inputs, if it is given, it will give you an answer which is. Now how do you represent this? If you know, OR gate is represented in a very straightforward manner like this, right? So this is your OR gate. What you do is you draw a line here, a curve here, and this will make it a exclusive OR gate, right? This is the way you need to represent it, exclusive OR gate. Okay, and this is your X, A, and this is your B. So this is a sign of and of course this is your output side, which is represented with this equation. Also in short form, it is written like this, right? Now let's draw the truth table of a XOR gate. Okay, let's draw the truth table. So this is A, this is B, right? So we are giving it 0, 0. There is no true input, which means there is no 1 in this. So the answer for this is going to be 0 anyway. The output of a XOR gate output is going to be 0. 0, 1, at least now you have one true and one is odd, right? So the answer is 1. Now 0 and, sorry, 0, okay, let's put it as, let me just change it and make it 1 and 1. Now it is being given even number of truths. Even number of truths, right? Two ones, even. 0. It only works when you have, when the number of true inputs is odd. So if you give it 1 and 0, you're giving it an odd number of true, which is 1. The answer is going to be what? The answer is going to be 1. So this is also a very important gate you will encounter many times when you do numericals of digital logics. But it is important that you understand the basics first, right? These all should be ingrained in your mind. The signs, the equations, the logic, how the truth table is built. Then we will do complex questions pertaining to this. We will obviously do simple ones and then gradually we will build on the concept and learn digital circuits, right?